continuation. So coming back to the last picture, right? So you see, we were writing the whole line as an affine combination of 2 points. So if we would like to write a plane in R3, we would need 3 points, independent points. And then affine combinations of those would just fill all the plane. But what about if we want to get only the segment from the point from A to B? Then of course that's also possible, and what we had to do is to limit the values of the parameters in the affine combination not to be negative, because if we restrict all the t's, t0 and t1 in our case, to be positive, then of course if they have to add up to 1, there must be all between 0 and 1, and that's exactly what fills your segment, right? And this can be done in general. In general, k-dimensional simplexes, so this will be one-dimensional simplex. So they need to get k plus 1 points in general position, which means that the generated space of all the affine combinations, the affine subspace, will be k-dimensional. That's it. And we write, so the triangle is a notation, my notation for the simplex, and the simplex is defined as the set of all the affine combinations which have got the property that the sum is 1. That would be the general affine combination, but on top of that we request that all the ti's are between 0 and infinity, but actually it means they are between 0 and 1 because of the other condition. So this is what we get. So in one-dimensional case we get a segment, so it's a one simplex. 2 simplex will be a triangle, but with the interior, right? So 4 simplex will be well, how it's called, this guy, with 4 equal triangles and so on. And you see that for simplices, for all the simplices, it's true that if we restrict to a subset of vertices, then there is always, I mean we can talk about the boundary, and the boundary, for example here, the one triangle on the boundary will be fixed by forcing one of the t's to be 0. And then what remains is a one-dimensional less simplex, of course, by the very definition. And this way you can get to all simplices on the boundary. Then the next level is you enforce 2 of those parameters to be 0, and you get the 2 codimensional bits of the boundary. So here you see, fixing 1 of them will be a triangle, fixing 2 of them will be one of the edges, fixing 3 of them to be 0, then the 4th one is enforced to be 1, and this will be one of the vertices, right? So we get the vertices, edges, and the triangles, the interior of the triangles. So that will be the subsimplexes, and this is a very nice combinatorial structure which again in many algorithms is used and is of big help. Right, so that's about the simplices. Now what about the convexity? So we say that a subset is convex if whenever, so there will be some subset M subset in say some bigger space, and what I want to see is that whenever I take 2 points there, then a line, so the segment between them must be completely contained in the set. That's the definition of being convex, right? Of course, if this was in the regular plane, then you see that I just break this condition here, so this set M wouldn't be convex, but there always will be a convex hull, the smallest thing which is already convex, and that would be something like this, right? And that's again something which is very useful in practice, because computing convex hull allows us to work then with data like being in the whole convex hull. So these small deviations, which are very often caused just by some noise or something like that, are removed, and with convex sets, many of the operations are much simpler, much more straightforward, much faster. So let's have a look at some examples what convex sets can be. So for example, an empty set is of course convex, right? So it's not a subspace, but all the conditions are true if there are no points at all. Say one point set is always constant. Yeah, so the smallest affine subspaces are always convex. All the affine subspaces are convex. All the line segments, all the arrays, right? So if you take a line, you can also say that you are interested only in going to one of the directions. So that's also convex. And more generally, if you take any k-dimensional object like this, which will be, well, on the line is half of the line. In the plane, it will be, what will be it? A quadrant, right? So you simply have two coordinates. So in a plane with coordinates, so you simply get all this, right? So the linear combinations of the points on the axis with positive coefficients. So why not, right? P is the origin. You can also take angles, right? So the angles will be taking two vectors. So it will be something like you take two vectors and you take any of their affine so this is again the P, and you take affine combinations of these 2 points where we request that the coefficients are positive. So it's something like this, right? The angle in the plane, but it will be in the plane is a special case. So it's actually a special case of the previous one. And there is a theorem which tells explicitly how to get convex hull, and it's of no surprise because of course what you take is you take your generating points. Yeah, so it's a subset M. You take the generators and you take all the affine combinations of the generators with the positive TIs, right? So this is like adding all the lines between all the couples of points, and if you iterate this, you finally get all the affine combinations, which is in fact the idea of the proof. So the proof is quite simple. So if you have a finite set of points in an affine space, then the convex hulls of those are called convex polyhedrons. Convex polyhedrons are actually a very nice thing, and it's used quite a lot also in combinatorics for some special kind of graphs, etc. Right? So here we are touching a really useful set of tools, although it's hard to see them before you use them, but please believe. So the convex polyhedron obtained from a finite set will be a k-dimensional simplex if and only if the defining points are in general position, right? So you see that if we just restrict ourselves to point in general position, which is an open condition, so if it's in general position, a small change doesn't change it. On the contrary, if you have points not in general position, then smallest deviation already allows you to make it in general positions. So you get exactly the simplices. Just a remark: if you use computer software to compute, and if you do it in reals with floats, so just the float reals, then essentially the computer will always consider them, more or less always consider them as in general position, right? So if you want to deal with something non-degenerate, please be sure you use rationals or some other means how to get there. Right. There are also special examples of polyhedrons. which are not of the generic type, but are very useful. And that happens, for example, imagine in a plane I would like to make a square, right? So I make the convex thing, which is defined by 4 points, but there are only 2 independent vectors there, and the other 2 are the same ones, right? Then, which bring us to the other points. Or in dimension 3, it would be if you get a cube, right? Then again, it's a different thing. But of course, we can also just make it with 2 vectors like this, and this is called parallelepiped. And the k-dimensional parallelepiped is just what we have here, right? So we have got k independent vectors, 1 point, and what we do is we just don't make all affine combinations, because we do not insist that the sum of the c's is 1. What we do is we just work only with a parametric description of our object, and we insist that the coefficients are between 0 and 1, and that draws you exactly the examples as I did here, right? So it will be, and again, as before, if you want to deal with one of the faces on the boundary, then you simply kill one of the c's and enforce it to be 0. If you want to get to one of the edges, you kill 2, etc. So, well, let me finish with very brief list of, well, it's just indication what the most affine tasks are. These are the individual steps you have to do in order to do something in the affine spaces, usual, like for example in computer graphics. So you want to change implicit description into parametric description. That's a very easy task. You simply take the system of equations and solve it, and get the general solution in the coordinates, and that's the parametric description. If you want to take several subspaces, like for example 2 lines in 4-dimensional space, or you want to find a plane given by a straight line and a point in R3. So that's typical task, and you want to define it either implicitly or parametrically, and that's always very simple because it depends in which form you have got the cues, right? But if, for example, if they are all given in a parametric description, then it's most simple, because you take the given points of all of them and add the differences of mutual differences of each couple of them as generators of your difference space, and you take a sum of the difference spaces of all the cues, and then in the end you pick one of the points from the cues and fix it as the origin for the parametric description, and that's it, right? And of course there are modifications if it's given different way. If you want to find intersection of subspaces, like you have got 2 planes in R3 and you want to find their intersection, again, if it's given implicitly, then you simply write all the equations together, that's it, and you cancel the dependent ones if you like. If you want the result parametric, you have to solve it. If it's parametric, then you can plug in the parametrization of one into the other and compute what happens, etc. Right? So there are several options, and it's quite straightforward, no problem. This is an interesting thing, so you can have higher dimensional analogs to that. Maybe I will draw a picture here that's nice. So you have 2 lines in R3, and then someone gives you a point P here, and your task is, well, so that was not a nice point, I can't then draw it, say a point here, and the task is to draw a line through the point which would meet the 2 lines, right? So that's called a crossbar. Or instead of giving the point P, you could instead just draw only to fix the direction of the line, so the difference space of the resulting line, and that's it. Right, so these are the standard tasks to do, and you can find all the description there. Maybe just to finish, so this is longer, I perhaps had to split rather the second presentation into two, but let me add some glimpses back to our linear programming task, because there I promise that we shall clarify some of the points why we can expect the solutions as we did. And the point is that if you take every single of the non-equalities in the definition of the problem, so you see that the allowed configuration, so the eligible points to look at the value function are actually describing a half space, right? Because if it was equality, it would be affine hypersurface, and if it's not, it's simply half of this, because you see that the function on the left hand side is linear, so for one half of the space it will be bigger than b, and for one half of the space it will be smaller than b. And you see the half space is a convex sink, and as we saw, intersection of convex sinks is always convex. So we know that the admissible configurations for the solution of the linear programming problem are always a convex subspace, and therefore for every 2 points all the segment between them is there as well, and we know that along each line the value function will either grow or decrease, and therefore either the minimum or maximum, whatever we are interested in, must be on the boundary, right? So now we have clarified the thing even much better than before we had the intuition. Now it's a proof. So thanks a lot. That's for this week, was the affine. No, there will be one more. This is the second presentation for the affine spaces, and one more will come.